Okay, so let us talk about those two problems. So I don't know who solved the problems. Do you remember the problems actually? So let me start with the second one. So if you remember, I don't remember exact diagram or picture, but this was something like this. I had a circle, then I had a line which is tangent to the circle at some point. Let me call it T. Hopefully that was the same name.
Yep.
And then I just randomly pick a point somewhere on this circle and then connect these 2 points together. Yes. Yeah. I don't know. Did I call this point something?
That point? No.
Yeah. No. So let us call it now A.
You called the angle something.
Yeah. So what is that angle?
Alpha.
Alpha. So let me call this angle alpha. And then we had here the center of the circle. Yes.
Yeah.
Let me call it O. And then connect these 2 points here. And then did I call something this one?
X.
X. And then I want to find the connection between the size of X, which is a central angle, and the size of alpha. Actually, Alexander solved the problem the same day, but let us see if we can find a way here. Okay, so you see here, this is also something, I don't know the English name for it, if there is an English name for that. So you see, this is not an inscribed angle, yes? Because, of course, the vertex is on the circle, that's good. One of the legs is a chord, but the other side is not a chord, is just one part of the tangent line. So it is not correct to call this an inscribed angle, because it is not, yes? But this one is still a central angle. Both of them are subtending the same arc. If I ask you what is this arc opposite to X, you will show me this part of the circle. If I want to say what is this arc subtended by alpha, again by convention you will say this one. Yes? But that is not important. The important is that if you have this scenario going on, what is the relation between X and alpha? That is what we want to discover. Okay? The method Alexander showed that to me, it's also working, but let us do it in a little bit different way. Do you have any idea what to do? Could you sleep before solving this problem?
Actually, yeah.
You slept better, yes?
Yeah.
No, but you shouldn't be able to sleep if there is a problem going on. Yes. Yeah. So how should we solve the problem? So let me give you a hint. One way is probably do this. This is the way that I was thinking about, but actually, as I told you, Alexander proposed a different way. So let me just continue this line so that this will continue and intersect the circle at some point. Let me call it B. So this dotted line segment was not in the beginning in the problem. So in principle, you should write it down. We continue TO, and then so that it intersects the circle at the point B. So you need to express it when you add something to the picture, the original picture in general. Okay. But now, how can we solve the problem? How this will help solving this problem? Let us give some names to these angles. For example, let me call this one angle U, this one angle V. Okay. What is the relation between U and alpha? You should be able to say that.
It's equal to 90 degrees.
Which one is equal to 90 degrees?
Both of them combined.
Combined. So it means that U plus alpha is 90 degrees. Do you agree?
Yeah.
Why? Because I told you that this is the very important property of circles. If you draw a tangent line and take the point of tangency and connect it to the center, it becomes a radius. That radius is definitely perpendicular to the tangent line. Of course, if this is 90, the other one is also 90. I don't want to mess up with the picture, so I would write it here. So alpha plus u is 90 degrees. What is the relation between alpha and v then?
Now, I was thinking that the triangle
Yes.
inside the circle,
Yes?
it is an isosceles triangle.
Yes?
Since both of the sides are the radius.
Yes?
That makes u plus v equals 90. No,
No.
u plus v plus x equals 180.
That's always the case. You don't need to have an isosceles.
Yeah, I was
triangle to
thinking
say.
that because u plus v are the same, that's
Yes?
just like 2u plus x. And, well, I thought that x is 90 because of that.
No, x is not 90. Might be in this picture it seems a little bit like 90, but in general it's not 90. If I have drawn this line from here, then you immediately see it's not 90, but
Okay.
the relation still will hold.
In that case,
Mhm.
maybe alpha is the same as v.
B,
V.
alpha is not the same as V. U and V are the same, as you said.
Okay.
You say OT is equal to OA. Both are radius.
Both are radii.
Yeah. Both are radii. Okay, so this is coming from here. So this implies that, as you said, U and V are the same. Okay, then what?
Baba,
Yes?
I have a question about, the intersecting point in any circle, the rule where you say that x is equal to 2 of the alpha, 2 alpha, right?
We want to come to that point. We don't know that yet. This is not an inscribed angle.
Yeah, but what if it is? What if it's on that point and just...
Now it is not. Okay, this is a new problem. This is not an inscribed angle, but I want to show that the same relation will hold at the end.
Yeah.
But it is not clear yet. Yes? So we want to show that again x is 2 times larger than alpha, even though alpha is not an inscribed angle. That we want to show. Okay? Okay, but we need to understand how. So u is equal to v, then what? So let me ask you one more question. If I add these, if I connect this point to that point, if I ask you what this angle is, what is your answer? So let me write another name for here. So let me call it, for example, T. What is the sum of U and T and Y?
I'm pretty sure that v and t together are 90
Why?
degrees.
So
Right
these
now-
are famous things. If you don't know them, it means that you will be in trouble. I talked about them.
Isn't this
This is a diagonal.
Yeah?
No, sorry. Diameter. That's a diameter, yes? So that's the diameter of the circle. And I told you, if you have an inscribed angle opposite to a diameter, that is always 90 degrees. You need to know this by heart. You also need to know the proof. We talked about that before. So from here, V plus T is also 90 degrees.
Isn't T equal to alpha though?
No? Is it?
Yeah, because u plus.
Yes,
because
T
u
is
and
equal
v
to
are
alpha. Yes, exactly. So it means that now what I do, I put instead of this V, instead of this U, I put V. Because they are equal, as Gustav said. So instead of U, I can put V. V plus alpha is 90. V plus T is also 90. So this means that V plus alpha is equal to V plus T. Then what does it mean? As you said, alpha and T are equal. Yes? So alpha and T are equal. But let me give this one a name. Y. What is the relation between Y and T? What is the relation between Y and T?
The
the same way you
They are exactly equal again, because OA is a radius, OB is also a radius. So this is an isosceles triangle. So T and Y are the same, yes? So it means that OA is equal to OB. This means that T is equal to Y. Okay, so this is number 1 and this is number 2. Comparing these two, what can I conclude? What can I conclude? Alpha and Y are the same. Yes? Alpha is equal to Y. Is that understandable?
Yeah.
Because alpha is equal to T, Y is also equal to T, so it means that alpha and Y has to be equal. Then more or less the problem is done. What type of angle is Y? Yes? It's an inscribed. What is the arc subtended by Y? Yes?
It's that.
Y is this arc, yes? So Y is half of X. Or by the way, you can write it, you can immediately see that X is an exterior angle. So X is T plus Y. T and Y are the same. So X is 2 times larger than Y. Yes? But Y is equal to alpha. So it means that X is also 2 times larger than alpha.
You lost me.
Yes?
Yeah, but how did you get U is equal to V? That's what I'm trying
I know.
So U equal to V is, as Gustav said, is correct. Because this is radius.
Yeah.
This is radius.
Sure.
This is radius.
Yeah.
Yes? So this angle is equal to this angle. This angle. Let me, by the way, let me do it in a little bit easier way for you. Might be this is a little bit confusing. So here, if I ask you what is the relation between Y and U, what do you say? We already know that this angle is 90. This is important, by the way. This you didn't know before, you learned it this year. That if this is an inscribed angle, why this is an inscribed angle? Because the vertex is on the circle, one of the legs is a chord, the other leg is also a chord. So this angle that you see here is an inscribed angle. But that is an inscribed angle opening opposite to a diameter. So this means that this angle is 90 degrees. This is very important to know. Yes, do you remember? I was talking about this before. If you have a diameter of it, if I ask you what this angle is, what is that angle?
180.
180. And if pick a point here and connect it here and here. This angle is inscribed subtending this arc. This angle is central subtending the same arc. So this should be 2 times larger than this angle. When this angle is 180, this angle has to be 90. This is the repetition of this reason. This is extremely important. These are simple facts, but if you do not train your eye for catching them immediately, then you will be in trouble. So you need to practice to catch these patterns when you see them. Yes?
So there's a way to solve this without drawing another triangle. It's much simpler.
Let us finish this one, then I will come to your solution. Okay? So what I'm saying is that because this angle is 90, if I ask you what is the relation between Y and U, probably this is the simplest possible case. We don't need to write so many things, yes? Even we don't need that one. So we just say this. You see, I continue this line, I connect this point to this point. Because of this rule, this angle is 90, yes?
Yeah.
And this means Y plus Y should be, Y plus U should be
90.
90. On the other hand, alpha plus U is
90.
90. So this means that Y plus U is alpha plus U, and then U is gone, so it means that Y is equal to alpha. So Y is equal to alpha. But what is the relation between Y and X? What is the relation between Y and X? X is a central angle subtending this arc. Y is a central angle subtending the same arc. So what does it mean? It means that X is 2 times larger than Y. Yes? And then Y is equal to alpha, so it becomes 2 times alpha. And you really don't need to even write this. Yes? So this means that this angle is again 2 times larger than this angle. So that's also an extremely important thing to remember, yes? If you have these kinds of angles, I don't know if there is an English name for that or not. I can probably check it later. But these kinds of angles are
That's
not...
always the case.
Yeah, that's always the case, yes. So it doesn't matter. For example, if you take this one, for example, I take another point here, I draw a tangent line here, if you can call it line, okay, and then I, for example, take some random point on the circle and connect it to here. This angle is not an inscribed angle. The vertex is on the circle, one leg is a chord, but the other leg is not a chord, it's a tangent one. So that's not the definition of an inscribed angle, but it enjoys the same property of an inscribed angle. It is important to know, okay? So, I don't know, for example, let me ask you one question now. If I connect this point to that point and connect this point to that point, if I call this alpha, if I call this beta, what is the relation between alpha and beta?
Isn't beta 2 times alpha?
No.
The other way around?
No.
They're equal.
Yes. They are equal. Yes. Because this is an inscribed angle. This is of this type of angle. I don't know what it is called. But you can imagine it in this way. You can imagine that this is the center of your circle. Now let me do it like this. I take this angle, I take this point and connect it here, and I call it x. Forget about this part. You should be immediately able to see what is the relation between x and alpha. What is the relation between x and alpha?
2 times.
X is 2 times alpha.
Um,
Central, inscribed, opposite to the same
the
arc.
opposite.
So central is 2 times larger.
Oh.
Yes? This is, we already knew about that. Today we learned something new. This is central, this is of this new type that I described it here for you. What is the relation between x and beta? X is 2 times larger than beta, yes? We just learned that. Both of them, 2 alpha is x, 2 beta is x. It means that 2 alpha is equal to 2 beta. So it means alpha is equal to beta. Yes, now I can hear your solution.
So there's a way to solve this without using the drawing out triangles. So what you say is that.
Let me just draw it here for you.
Yes.
So I have this one, and I have this tangent line. So let me give the same names that you can just talk to me. So here, so this is the original picture. Here is alpha, and here is the middle point. So let me just, this is, that's not a good shape. So this is not 90, so let me call it x. Okay. Now this is O. Okay, what should I do?
Yeah, okay, so to start up, you do also need to draw the other angles V and U.
So here U,
Yes,
And
like
V.
you did on the other one. So we know that 8 alpha plus U is equal to 90 degrees.
yes.
And we also know that it's an isosceles triangle, so V is equal to U.
That is okay. That's the starting point. Yes.
So we can say that x plus 2u is equal to 180.
Yes.
And then we can also say that 2 times alpha plus u is also equal to 180. So then we can write that x plus 2u is equal to 2 times.
Yeah, it's much better. Yes.
Yeah.
Thank you.
And then
So x plus 2u is equal to 2u plus alpha. No, 2u plus 2 alpha, because if I multiply 2, and this 2u and 2u are gone, so x becomes 2 alpha. Yes, thank you very much. Probably it's much better than my solution. Yes, thank you.
Hold up now.
Because what he's saying, he's using the same fact. So he's saying that alpha plus u is 90. So we know that these two are the same, of the same size. So it means that this is an isosceles triangle. It means that u and v are the same. So what we need to do, we write this in this triangle. X plus U plus V is 180, but U and V are the same. So if I add them, it becomes 2U is equal to 180, yes? Now, because this is 90, I can multiply this by 2. It becomes 2 times U plus alpha is equal to 180. This is 180. This is 180. So this one and this one have to be equal. But if you multiply 2 inside, it becomes 2U plus 2 alpha. 2U and 2U are cancelled. We get, thank you very much. This is much better than my solution. Okay, so that is x equals to 2 alpha. Yes? Is that understandable? Okay, good. How should we solve this problem? I remember that the notion of the exterior angle should play a role here as well. So, for example, we can take the ruler and connect these 2 points together. Okay? B and C. Or it might be the case that you want. I think in this picture it's better to connect A and B. Let us do that. Okay. So let me do that. Okay, so this is, I am adding, in principle, if this is an exam question and you add something to the picture, you need to explain it in words. Okay, so you need to say that, okay, I connect D to A. This is something that you need to write down, okay? And then, it's actually a very simple problem. I was confused myself last time. So this, let us call this angle something. I don't know, for example, we can call this big angle Y. But hopefully you realize that this is an exterior angle to one of the triangles here. Can you see which triangle is that? So this is the only thing in geometry. You need to train your eyes, and it is not easy. For example, you saw that yesterday I myself was confused. I couldn't find this very simple thing. Yes?
ADM.
ADM. That is an exterior angle to ADM. And then after detecting this with your eyes, you need to remind yourself about what you know about an exterior angle. So if I ask you what do you know about an exterior angle, you know that the size of the exterior angle is equal to the sum of the sizes of 2 internal and interior angles which are not adjacent to this. So one of those interior angles, I hope that you agree with me, it is x. Yes? Okay, so y is x plus what? Plus what? Yeah, it's easier. Okay, so how should I do that? This becomes plus gamma. Okay, and then now if I ask you, what is the relation between gamma and beta? This you should immediately detect. I cannot help you more than that. Then what's the relation between gamma and beta?
They're equal,
No.
but they're sharing the same arc.
Yes, but one of them is
central.
central, the other one is inscribed. Yes? Yes? So I think your energy is actually declining, yes? I have several times repeated this. This is simple, so probably the last exam would be very problematic for you. But be careful not to fail. If you fail the course. There is no other time to repeat that test. Yes? Be careful about that.
Yeah,
It's on the week 22, the more or less the last moment. Yes? Be careful about that. So x plus y, and then I really want you to solve most of the problems in the book as much as possible. And then do it level 1 problems from the beginning to the end and go back and solve harder problems. Because you need to guarantee that you can pass this. Unfortunately, that's a bad time. Even though we continue, but the grades should be set in the 3rd of June. And I need some time to prepare the grades and everything. So Monday, week 22 is the last day of exams. Yes? Be careful not. Yeah. So x plus gamma. Okay, so now let us talk about this. So you said that. Okay, let me do something like this. X is x. Instead of gamma, what can I put in terms of beta? Beta divided by 2. Yes? And what can I write for y? It was so simple, you see. What was y? So y is equal to x plus gamma. And then because this is an exterior angle, x plus gamma. And then I'm asking you what is the relation between gamma and beta. Beta is a central angle. Gamma is an inscribed angle. Both of them, they are subtending the same arc. So this is half of this value. So this, instead of gamma, I can put beta over 2. But what can I write for y? Yes?
Half of alpha.
Half of alpha, yes, because y is an inscribed angle subtending this arc. Alpha is a central angle subtending the same arc. So it means that y is half of alpha. As simple as that. So you see, I myself was so confused. The problem is finished. I want x, so I move this to the left, yes? Alpha over 2 minus beta over 2 is your x. Yes? Lesson is similarity. In principle, you have studied this actually, I don't know, 3 months back, so you should be able to remember it. So, similarity, okay? Okay, so what is the meaning of similarity? Let us talk about triangles. When do we say two triangles are similar? Yes?
It's when they share either two angles or if there's that relation between the sides when you divide.
No, those are theorems.
Okay, it means there's a resized versions of
Yeah,
each other.
exactly. So that is meaning, so I don't know, you zoom in, zoom out, what you are happening, nothing is changed. So the main point is that the angles are preserved. This is the important thing. Even if you have your picture and then you make it bigger, if you take, for example, I don't know, the points on your eyes and connect it to your nose, and then measure the angle between those, in the bigger picture and the smaller picture, this angle is the same. Yes, the length are different, but that's the meaning when you say two pictures are similar. So do you understand what I mean? So you have your picture and then you make it bigger in size. You drag it and it becomes bigger. This picture, new picture, is a similar version of the previous picture. Even though the size are different, but the angles are preserved. The corresponding angles between any 2 points are preserved, yes?
But the sizes of these triangles are also proportionally going up and down, like between the...
Yeah, that is if it is not the case, then you will see a different face from you if the sizes are not proportional. But the main point is that the angles are preserved, yes? Yeah? But, so in principle, if I want to draw, of course, drawing these things by hand is a little bit hard. So for example, if I consider this triangle ABC, and let me, for example, try to, yeah, so something like this. These two triangles are called similar triangles, yes? When I say that these two triangles are similar, there are two conditions for that. So it means that the corresponding angles are the same, yes? B is equal to B prime, and C is equal to C prime. And then this is not enough. One more thing is necessary. What is that? The ratio of A prime over AB, and the ratio of A prime C prime over AC, and the ratio of B prime C prime over BC, these three fractions should be the same. So how many conditions are needed to check if two triangles are similar?
6.
How many? Yes?
Well, if one of these is true, then the other one will be true,
No,
right?
in general. We don't know the theorems yet. Put yourself in that position. That's the definition of similarity of two triangles. If I want to check that these two triangles are similar, how many conditions you see here?
6.
No, then the number of equalities. 1, 2, 3, 4, 5. So there are 5 equalities that we have to check. Because, for example, if I check that these are equal, and check these are equal, then automatically these two become equal, yes? Okay. So this is not 3 conditions, this is only 2 constraints, because we have 2 equalities, and we have 3 equalities here. So in principle, I should check 5 equalities, yes? To guarantee that 2 triangles are similar. If one of them, even one of them does not work, we say that these two triangles are not similar. Is that clear? And this is not something, by the way, you forget. The thing that I mentioned, especially these days that everyone working with computers, it is a very easy thing that you resize your picture by dragging it, yes? So you are producing similar objects. And it shouldn't be hard for you to critical thinking about this. If you forget, you need to understand what is the meaning of similarity between triangles. Okay. But for example, it is automatically clear I really do not need to check all of them. Do you agree? Because for example, if I check the first pair of angles and they are equal, do I really need to check the third one?
No.
No, because the third one automatically becomes equal. Why? Because the sum of the angles should be 180 regardless I am looking at this one or that one. Yes? So it's clear that, for example, if I have the equality between these two, the third one automatically is satisfied. But it is not clear that these two are automatically satisfied as well, but surprisingly, yes, they are. And unfortunately, in the book, they don't want you to know about why this is correct or not, so let us just memorize them. Okay? There is no time for explaining them in detail. So, this is the first thing. In principle, if you want to check two triangles are similar, you need to check all of them, but there are two theorems. So let me write THM1, theorem 1. If two angles from one triangle are equal to two angles of another triangle, of course it is not surprising at all the third one should be the same, but it is not trivial at all that why these conditions also hold. Is that understandable? So this is why you need this theorem. If you forget this theorem, there is no way, unless you are a very, very genius person, you discover everything on the exam. Yes? Okay, so be careful. If I know that these two angles are the same, I completely immediately understand without thinking that much that the third pair should be equal. But if this ratio is equal to this ratio, is equal to this ratio, based on only this piece of information, is not trivial at all, and that is the content of the theorem, making your work easier. This tells you that just check two angles from one triangle with the other triangle. If they match from size point of view, don't worry. Every other condition that you need will automatically satisfy. Yes? So that is called two-angle theorem. Yes? And the other theorem tells you that you don't need to check the angles at all. You can just check these two conditions. If it is met, the angles automatically become equal correspondingly, which is not trivial again. So the other theorem tells you that the ratio, so let me write it in this way. Two angles implies that let me write it very simple for you. So equality of two angles implies similarity of triangles. Okay? So the only thing that is missing is the proof, which is actually the most important part. Theorem 2 tells you that if the equality, so here I should write the equality of the ratios of the ratios of the corresponding sides. Let me write it simpler. The equality of the ratios of the sides again implies the similarity of triangles. Okay, so these two theorems, we talked about them in Math 1C as well. So this is what I want you to understand. Don't memorize them. Of course, at the end you have to memorize them because I told you it's not trivial. So this is called angle theorem or two angles theorem, and this is, I don't know, there is no particular name for that. Most of the time, this is the most important theorem that you need to know. If you want to show that two triangles are similar, the first thing comes to your mind should be, can I convince myself that two angles from one of the triangles is equal to the two angles of the other triangle? Most of the problems, 90%, I think nearly 100% of the problems in the book relies on this theorem for similarity. Okay? Okay. But most of the time, you want to explore the consequences of the similarity of two triangles. For example, let me pick some examples from the book to see how this will go. So, for example, these simple questions you need to know. Okay, let me just use the book for example. So, there is a triangle here. I told you this is very hard to draw them precisely on the board, but this is given 56 degrees, this is given 42 degrees, and then there is another triangle drawn in that way. Yeah, something like this. So I would say that the figure is not to scale, so the shape is not to scale. So, but let us write it something like this. E. And then they have given this angle to be 42 degrees and this angle to be 83 degrees. Okay. Now the question is that, do you think that these triangles are similar? So do not rely on your eyes, because I was not able to draw them precisely. So just look at the pure information. So do you think that these two triangles should be similar?
No.
Yes or no?
I think so, yeah.
Why? Because of course this angle is equal to this angle. Can I show that another angle is equal to another angle of this one? Of course it is clear that this one is not equal to this one, but just right now you cannot say that they are not similar, because who knows, might be the third angle is equal with the third angle. So it means that you have to calculate this if you want to say no. Before knowing the size of this and this, you cannot immediately jump to the conclusion that they are not similar, yes? Okay, so let us calculate this angle C here. So what is angle C? It is 180 degrees minus what? 56 plus 42. 100. What is that one?
100.
100.
Yes.
Or is it
No,
48?
it shouldn't be 100. If you want to say me something, please tell it right, okay? So this is 98. Yes? And if you subtract them, how much? It becomes 82 degrees. Yes? Okay, so now we know that this is 82 degrees.
No.
Yes or no?
Yeah.
Yes?
Yes.
Yeah. So this is 82 degrees. Okay, now can I conclude that they are not similar?
Yes.
Yeah.
Why?
Not similar.
They're not.
They are similar or not similar?
They're
No.
similar.
They're not.
What? No.
No.
So that means
So what is, if you want, you can calculate this one as well, but what is this angle? It's 180 minus 42 plus 83, yes? So this becomes how much? 125, and this becomes 55 degrees. So this is 55 degrees. Okay, can I find two angles from that equal to two angles from this one? No. So they are not similar. Okay? They are not similar, so this is a very simple question. Okay, but there is another good problem here. So let me just draw them based on the next view. So there is a triangle given, this is problem 4224. A triangle with these numbers, with these sides are given. So forget about drawing it into scale, okay, to scale. So this is one of the triangles. The other triangles is a little bit bigger with these sides, 25, 19, and 14. So we want to see that if these two triangles are similar or not. So if the question is similarity of these two triangles, which one of these theorems seems more reasonable for this context? The first one or the second one? Just say it.
Second.
The second one, because we don't have any information regarding the angles. Okay, but of course, later there is some rule, it's called cosine rule. You can learn it in Math 3C that we can calculate all the angles. But forget about that. Here I have this information. I want to see that if these triangles are similar or not. So the equality of the ratios of sides, Do you remember I wanted to write corresponding sides and things like that, which is important. So how should I know that? There are plenty of ratios that you can play around, but you cannot check all of them. If you have enough time, you can start randomly checking all the ratios to see if this is... Because if the equality of one pair of ratios are correct, then we can conclude that these are similar. But you need to order them regarding the size. The smallest number here is 8. The smallest number here, the second one is 11. And the third one is 14. Okay? So then you draw some fraction lines between them and then put question marks. So if you have chosen the smallest one for the numerator of the first ratio, for the denominator of the same ratio, you need to choose the smallest one from here. Yes, what is the smallest one?
14.
14.
Is that a rule?
Pardon? Yes, this is important. If you don't do this, let me see what type of answer we get from here. So from 11, this is the middle one. The middle one is 19. So I put 19 here. And then what should I put here? 25. So of course, the third one I really need to check at all. Yes? Because the first one doesn't work. So even if the third one works, it doesn't work for all of them. So here I can conclude that they are not similar. Yes? Because 8 over 14 is how much? So by the way, how do you understand it immediately? Do you remember? Please remember this rule. I will freely use them without explanation from now on. I need to work on your memory, okay? So how do you understand that this fraction is equal to that fraction immediately?
Can cross multiply.
Yes, that is called the product of means is equal to the product of extremes. A times D, B times C. If they are not equal, this equality does not hold. So you can take your calculator and multiply these two, so it becomes 154. And if you multiply that, it becomes 170, 152, I think, yes. Am I right?
Yes.
Yes, they are not equal. Because they are not equal, it means that these two, this question mark is no, false. When this part is false, I really don't care about the last one. But if this was true, I have to check the last one as well. All of them should be the same. If all of them are the same, then I conclude that these triangles are similar. Yes or no?
Yes.
Okay. But these are minor things. The important thing is that to prove something out of similarity, these are hard questions. Okay, so you need to learn how to use them. Especially we use this part. If I can convince myself two triangles are similar, it means that I have the guarantee of these ratios to be equal. And then I can find a relation between the length of the sides of one triangle with the length of the side of the other triangle. So this is the general strategy behind powerfulness or strength of similarity. So similarities, especially in triangles, are used to discover relations between the length of sides of one triangle with the other one. Yes? Yeah.
Will we use similarity of triangles within circles?
Yes. Yeah.
Damn.
We will use that. Okay, so far, do you have any questions?
Yeah.
Okay, so let us now, for example, this is a very simple problem. I think it is missing now in the book because it was in Math 1C. It's a very instructive example. Let me just talk about that for you here. Okay, so for example, let us consider a right-angled triangle. This is a right-angled triangle, for example, ABC. And what I do, I draw one of the heights, this height actually. There are three heights. One of them is this one, the other one, this one. I draw this height here.
Right, this question.
Okay? So this is actually a prototype example when it comes to similarities. Okay? I call it AH. So I have a right-angled triangle from the beginning and I draw its height. What I want to show, for example, it is not trivial. I want you to understand the power of similarity of triangles. So you see AH has a length, okay, and this one also has a length, BH. This one has also a length, for example, CH. I want to show that if you draw a right angle triangle and draw its height, it doesn't matter where you start, it doesn't matter which right triangle you choose in the first place. The nice relation between them, if you multiply the length of these two line segments, it becomes the length of this height to power 2. Okay, so this is, you see, it is not trivial at all. So if you have a right angle triangle, how should I know this? So if I ask you what type of relation is that, you would say that is the type of relation between the length of different parts. This is not regarding angles. I am trying to say something about the size of different parts of this figure. Okay? One way to do this, whenever, this is by experience, I'm not saying that this always solves all the geometry problems related to length of sides. No, but one way, one prototype way of thinking about this is thinking about similarities. Okay? So it means that I need to convince myself two triangles here are similar. Of course, how many triangles you can see? This is one of them, this is 2, and then 1 is the third one. So how many similarities I can talk about? I can talk about 3, yes? For example, this one with that one, this one with the bigger one, this one with the bigger one. You can still sit down and patiently try all of them to see if one of them works or not. But it takes time. So you need to have a little bit of wise plan from the beginning. So look at the relation that you want to prove. Okay, so let me highlight them. AH, let me highlight it here. So this length should be involved. Yes?
Can't you just use angles too to solve this question?
No, we haven't
Not
reached
that.
to that point yet. Okay.
All right.
BH is this one. CH is this one. By just highlighting them before starting, if there is a chance, look at my sentence, listen to my sentences. If there is a chance, we don't know yet if there is a chance for this. If there is a chance that I can solve this problem using similarity, which pair of triangles is more reasonable to think of, to start with? Which triangles? Yes?
Triangle ABH and ABC, or no, AHC.
AHC. Yes? This is more reasonable to start. Why? Because you see that this leg and this leg are involved. This leg and this leg are also involved. So it is more natural to think about similarity between these two instead of thinking about the similarity between this one and the bigger one. You understand me? You need, of course, you can still try to do whatever you want and say this doesn't work, cross it over and try another one. But this is not a wise way to do things. Okay, so now you see that you want to convince yourself, if possible, there is still a big question mark. Can I convince myself that these two triangles adjacent together are similar?
Yeah.
But okay, now I'm listening to you. Why they are similar?
Then you can try.
No, why they are similar first. You cannot presuppose they are similar. If you do this, you will lose points. You need to tell me why. If you want to use similarities, you need to prove they are similar. You cannot say that I feel they are similar, so this is my argument. Why they are similar?
You can call that 90 degrees to M and N. Call them. Then you have the.
So let me
angle
call
of
this
C,
one, for example, U and V.
U and V. Then you can call the angle of C to W, right?
W. Okay.
Yeah, sure. Then you have, you have U plus V. That's 90 degrees, right?
Yes, U. So let me write. Yes, that's
Yeah.
correct. So let me write.
Then you have.
So
V,
we say that U plus V is 90.
Yeah.
And then one more.
Then you have V plus what is it called? Is that
You called me W, yes?
W and then V. It's 90.
Yes,
Then you
what-
have an equation system.
Yeah,
right
thank
there.
you. You don't need to. So yes, that's correct. Technically, it's equation system. But here you see that U and V if I add them, it becomes 90 because the triangle is a right angle triangle in the first place.
Yeah.
But now look at this triangle. This angle plus this angle plus 90 is supposed to be 180, but this is 90. So what is left for this is again 90. Yes? So now you conclude here that, so you see you need to write all of these things. You cannot say that I consider that they are similar. No, you need to prove the similarity first. And then you see that this one and that one are cancelled. Why they are cancelled? I move one of them to the left, the sign will become negative, they will cancel. So U is W. But it is not finished yet. Okay? Because this is one angle. How many angles I need? To convince myself 2 angles. And then you should properly write it down. Okay, so what is the other angle?
It's 90 degrees angle.
So this is 90 degrees angle, yes, because, so let me call it like this. Usually if you have the same vertex, so let me call this one H1, for example. But immediately you realize what is happening on the left-hand side, it's also 90. Do you agree? Because if this is 90, this one is also 90. So you would say that H1
Then they
is
both have
equal to
90.
H2 is equal to 90.
Yeah.
Now you need to somehow write it and convince me. From these two, I can immediately conclude based on angle. This is enough. We have this convention. When you write this, I understand. You don't need to explain too much. Angle theorem tells me that which triangle? Triangle AHB is similar. This is the symbol we use for similarity. Is similar to the triangle AHC. Yes? So this is crucial. You cannot you just say that they are similar. You will lose some parts of the point of the exam. But here, when I know that the triangles are similar, this is usually the hardest part. You shouldn't get confused to write the correct ratio. Okay? And I really want you to rely on your imagination, because you have done these things probably with computers a lot these days, so you can imagine. Imagination is the easiest way to write it down correctly. What do I mean by imagination? Take this triangle out and rotate it and put it back here. This is the best way. It's not hard, yes? Because, so let me draw this triangle. This is the way that I imagine it, for example. If that is exactly AHC, I take ABH out and rotate it to make it similar to this in the correct way. So then, can you tell, yes, I just rotate it, and so what is this angle again? This is H. Can you tell me what is this vertex?
B.
It's B, yes. And then what is this vertex? It's A. Yes? I think this is the best way to understand. It's not hard, yes? I take it out and rotate it. How should I rotate it? What is the rule? The rule is to fix the angles the same. This angle is the same, this angle is the same here, and this angle is the same. Make the angles correspondingly beneath each other. And then writing this ratio is very, very simple now. So, you want to write. If I want to write all the ratios, how should I write? For example, choose one of the triangles, the bigger one or the smaller one, it doesn't matter. Okay, so let us start with the smaller one. So if you are not experienced enough, might be you want to spend some time to write all of them. No problem. So take BH, for example, from this one. It doesn't matter which one you start with. Let us start with BH. When you write BH on top of that, you are restricted to write one single thing below that. And what is that one? If I choose BH from this, I have to write AH below that. There is no other choice. Okay? So I consider this one and consider that one. Now let us go to the next one. AH. If I write AH, and by the way, I started with the smaller one in the numerator, suddenly you cannot choose the bigger one in the numerator. Whatever you want to, you have freedom, but you need to stick to the same rule until the end of writing this down. So this becomes AH. If I write AH from here, because the reason that I am telling you don't get confused, because AH appears here and there. Okay, but this AH is which one of them? Is this one for the lower one, yes? And this AH is for the bigger one. Okay, and then what should I write below AH here? What? What should I write? CH. And then, of course, it is done. You don't need the last one. But let me write the last one. What should I write for the last one?
BA.
Pardon?
BA
BA
over AC.
AC, yes. But you see that I don't need that one. It is true, but I don't need it. Because what I need is between AH, something between AH, BH, and CH. So it means that I just take this one, which I need. And then I use the same rule. This multiplied by that is equal to this multiplied by that. Yes? But AH multiplied by AH means AH squared. And then BH multiplied by CH. And that is the proof of this. So it means that we were able to show that this is always true in a right angle triangle. Is that clear? Yes? So these technical things, I don't think this needs more explanation. You exactly know. It might happen that I myself cannot detect a pattern or I could make mistakes. But this is what it is. So you need to understand how to write these things. It might be extremely hard. But hopefully you don't have that extremely hard questions in the book. And there is something bad in Swedish books is that, first of all, usually when you want to refer to the size, when you write AH, in geometry we mean the line segment AH. So that's a figure, that's a shape. And then what is the meaning of raising a shape to power 2? It doesn't make sense, yes? But it is important to understand, when you see a power 2 on top of AH is not the shape, is the length of the shape. If you understand that, there is no matter of confusion. But in British or American books, they write something like this. If they write this, they mean the length. If they write this, it means the line segment. So they differentiate between these two. Of course, we have to differentiate, but the philosophy behind this Swedish system is that the differentiation is clear in the context. Yes? I cannot say that this is a line segment, which is a line segment. I am multiplying the line segment by another line segment, because multiplication is between two numbers. So when I see this multiplication, I immediately interpret this as the length, not as the line segment. I myself also prefer to use it in this way, because then we don't need to write so many things. Yes? But you need to understand. So here, when I write BH divided by AH, it's completely clear I am taking into account that these are numbers. Otherwise, I cannot divide, for example, a triangle by a rectangle. It's meaningless, yes? Is that understandable?
Yep.
Yeah.
Okay, let me ask you another question here. So try to understand it in a better way. So let us not leave this problem yet. Let me clean everything here. I am asking you to prove something more for me here in this right angle triangle. So let me see if I can remember what is the relation. So let us, for example, I want you to prove for me that AB squared is equal to BC multiplied by BH. Okay, so that's also an extremely important property for right angle triangles.
Is it for the same triangle?
For the same picture, yes. Exactly the same picture, but I changed my relation. I want to prove another relation. I want you to go through all the details, yes? Think about it. Because there are three pairs of of similar triangles here. Which one is more suitable? How should I convince myself first that what I claim about similarity is true? Everything should be included in your answer for the problem. I think this is from pedagogical point of view, this is the extremely good problem. So let me just pause this video. Let me ask you. I don't want to solve it myself. If there's a big if, of course. If this problem is supposed to be solved using the similarity idea, which pair of triangles is most probable ones to think about? Yes?
ABH and ABC.
Yes. Why is that? Because at least I can highlight the line segments involved in the problem. One of them is AB. So let me take out these highlights here. Okay, one of them is AB. So let me highlight this leg. So far we don't know because this is both a leg for the bigger triangle and then the leg for this one. Probably that is enough to understand, yes? Because this is involved 2 times, yes? And then you see a power of 2 there. So it's somehow related. AB is the leg of 2 triangles. It is the normal leg of the bigger triangle. And it is the hypotenuse of this triangle. So might be it's a good idea to think about this small one and this big one instead of randomly trying all of them out, yes? Okay, and then of course if you want to, you see BC is from here to here, so it more or less confirmed that our guess is correct because BC is for the bigger one again, and BH is for this smaller one. So by this checking things, you immediately realize that you need to focus your energy to prove that this small triangle is similar to the bigger triangle. But I would say similarity in this case, proving the similarity is easier than the one Hussein did. Here it's more or less trivial. Can you tell me why these 2 triangles are similar? Why this smaller triangle is similar to the bigger one? Yes?
Yeah,
please, yes. Share one angle and the other angles are equal. Yes, that's better. Because they share this B exactly. Do you agree? This B is an angle for the smaller one, and it is also an angle for the bigger one. And then one angle you see, how much is this H2? Is 90. What is the angle of A? It's also 90. But you need to write it down, okay? So you would say that B is equal to B, something like this, common angle. Or you can write it in your own words, common angles, yes? And then I would say that angle H2 is equal to the whole angle A, but because there is a matter of confusion which one is A, let me write BAC, yes? There is no matter of confusion here. BAC is equal to 90 degrees. Then you need to write something like this, curly bracket or whatever you like. But up on this arrow, it is always better to mention angle. When you write this, I understand that what you are referring to. This is angle theorem, yes? Then this means that the triangle ABH is similar to the triangle ABC. Now, if I want to use this idea, I am allowed to use that. But the hard part is again this part, but I don't think it is hard for you to realize it immediately. So, you can imagine it in your head. How? I bring this small triangle out and I put it on the paper or on the whiteboard in a way that the corresponding angles match. The corresponding angles are beneath each other. So can you tell me, so you see, I bring it out, how should I draw it? I want to match it with this.
Yeah, BH.
So I draw it here and then you give me the names. This one, I bring it up and I flip it here. So can you tell me what should I call this vertex? Which vertex is that?
What does that mean?
What is the name of this? H. What is the name of this one?
B.
Let me think. Yes, that's B. And what is that? This one? It's A. Okay, so you need to draw this in this picture or think about it. Is that understandable for everyone?
Yep.
Yes? So I bring it out and rotate it. Whatever you want to do it in your head, that's your head. But then you need to write the correct thing out. Okay? So what should I write here? Now compare them. For example, you see I need AB. And by the way, you don't need to write all of them. Just try to understand which one is necessary. AB is involved in this relation. BC is involved. BH is also involved. Okay, so let us start with BH. If I write BH, below it, what I have to write? AB, because this is AB. Yes. And now go to the other one. I need to somehow BC be involved as well. But BC is for the bigger one. So let me write BC below this. And then what should I write in the numerator? AB. Do I need more? No. Because this will give me the relation that I need. Yes? AB times AB becomes AB squared. And then BH times BC. Or BC times BH. It doesn't matter. And then you get this relation.
But would it be wrong if you wrote AB divided by BH is equal to BC divided by AB?
No.
Yeah.
So you want to write from one triangle to another triangle. Yeah, if you write, that's okay for me. But when I am teaching it, I don't want to confuse people.
Yeah.
I prefer to choose one of them from one triangle, the other one from the other triangle. So is that okay?
Yep.
Okay, I don't want to solve the other one. You can think about it at home, but it is trivial. Which pair of triangles we need to take into consideration this time? AHC with the bigger one. But let us explore the consequence of these two relations. Do you see what can I conclude from these two relations? So please do it at home. If you don't do it at home, you will forget. We have a short memory, we have a long-term memory. Short memory only works for 12 hours. If you do not study in 12 hours, 90% of that you will forget. Unless you have an exceptional memory, okay? Yes?
But is this good to know for the test, like this theorem or whatever we call it?
No, if you want to solve harder problems, yes, I have them in my memory.
Okay.
But I don't give you any questions that you need to have this in your memory to be able to solve that.
But it's good to know.
Yes, yes. If you want to solve harder problems. Okay, but let us explore the consequence of these two relations. Can you see what is coming out from these two relations? So let me clean this one. We don't need them. No, we need the picture. So let me clean this one. Let me add them. Might be you ask why, but let me add them to see what's happening. I add them side by side. It becomes AB squared and plus AC squared. On the right hand side, I have to add this one with this one. So it becomes BC times BH plus BC times CH. Yes, do you agree? I can add them side by side. But can you see what's happening now? What can I do? What can I do more on the right hand side? No, that's not 2bc. This is algebra. You see, x times y plus x times z. This is not 2x. What can I do here?
Factor out.
Factor out. So here I can factor bc out. Yes? So this becomes equal to bc. What is left from the first one? bh. What is left from the second one? ch. Yes? But is there any better name for bh plus ch? It's BC, yes? Look at the picture. BH plus CH. How much is that? It's the size of BC. Do you agree? So I can write BC is BC. If I ask you what is a better name for this, you say BC again. But BC plus times BC is? BC squared. So this is Pythagoras theorem. Yes? So AB squared plus AC squared is BC squared. So that is another proof for Pythagoras theorem based on similarity of triangles. You understand? So I don't know if you remember, we had a little bit complicated way of proving the Pythagoras theorem in Math 1C. So do you remember? I start, if I give you a triangle, then do you remember? I start copy and pasting it 4 times, like this, if you remember. What was that? Yes. And then something like this. So it was a harder proof. So this was my triangle in the beginning. I wanted to show that C is A squared. I wanted to show that A squared is B squared plus C squared, yes? Then I copy and paste it 4 times in this strange way. And then we talked about the areas. and we realized that a squared is equal to b squared. If you have forgotten, you can go back and watch the video, or you see it in the book. So it was a very strange way, but very creative way of proving the Pythagoras theorem. But that is also another independent proof of the Pythagoras theorem here. We were able to prove the Pythagoras theorem using similarity in this context. Yes?
What does O dot O mean? By that?
No, this is not O. A dot A means angle, angle.
Sure.
Angle, angle theorem. Instead of angle, angle, let me be lazy and write AA. Okay, so that is also a nice problem here. Any questions? Yes?
Well, yeah, can you use common angles for a number of things that, like you did there? I tried it and I got common angles of AA and CC.
I don't understand your question.
Like for question 3.
Yes,
The
for
common
question 3.
angles
Yeah.
A. And
Yeah, that's
C.
the same story. But doing it on the other side. Yes?
How many proofs are there of the Pythagorean theorem? I heard there's like over 100 or
Yes,
something.
it is. Yeah. Yeah, it's called the Bright theorem for something. Yes, and there are many proofs with it.
So-
But that's extremely important in our universe.
So maybe like when we're bored on the remaining lessons, if there are some proofs we could understand, maybe
Yes.
you could show them.
I don't know all of them, but we can
Maybe you
Google
could look
around.
up, and if there's something that we could understand at our level, then
Yeah, might be. I think all of them are at your level. Might be
all
there
of
are.
them.
I would say so if this is based on geometry. If they are based on because Pythagoras theorem is so fundamental in our universe. If Pythagoras theorem holds, it means that our universe is somehow intuitively flat.
Well, can we have a mega marathon where you show every proof of the Pythagorean theorem?
No, why would you
Proof
have that?
marathon.
No, it's not.
Proofs are done, so what should we do with the lessons either?
Have you seen this guy on YouTube who has done like 100 integrals in like an entire video? It took him like 6 hours or something.
No, integrals I am a fan of it.
Oh, okay.
Yeah,
But
I myself, because integrals, you need to be, because the results you get is also very interesting. But Pythagoras theorem, at the end of the day, you know the result.
yeah, but you can do the same thing for proofs. Do 100 proofs in one video.
I'm not interested in that. If you are interested, you can set up a YouTube channel on your own
Well,
and try to discuss
Well,
about
I'm not a fantastic math teacher, so maybe it would.
So I'm not interested, at least, in proving that. Anyway, let me give you another. Well, we are here, but let me give you another relation. This I want you to discover. Now you are working, you are thinking in similarity. Let me ask you one question. Can you tell me why this is correct? I want you to show me that AB times AC is equal to AH times BC. Let me call this number 4. So these are 4 very important relations among the different lengths that appear in this picture. So we have this. It's extremely important to know that. So if you draw this, you have this formula. You have that formula, that formula. By the way, this is 5, yes? There are 5. 1, 2, 3. Pythagoras theorem itself, number 4. And this one, number 5, if you want. So there are 5 very interesting relations between the different parts of this shape here. Okay? But because Pythagoras theorem is so famous, let us consider it 4. Why it's correct? Yes, Cameron?
Well, because they both describe the area.
Yeah, because now you are working, you are thinking about similarities, you are trying hard to make the similarity works, but suddenly the similarity does not work. So this is why this big if, I'm telling you that, if this problem is going to be solved using similarity, don't try everything out. Be wiser than that, okay? But I don't know if we can prove this using similarity. Do you see a pair of triangles which is suitable for our case? And then I describe what Cameron said actually. It's so simpler, much simpler, yes? So do you see any similarity that works here? We have AB, which is this side, and then we have AC, and unfortunately we have BC. So, and then I have AH. So might be this also works, yes? Don't you think, Cameron? So similarity will also help to solve this. Yes, but that method that Cameron mentioned is easier than similarity. What was Cameron mentioning? He said that, okay, let us calculate the area of this triangle. Okay, one possible way of calculating the area is to write the base times the height divided by 2. So this, if I ask you what is this, you would say this is the area of this triangle. But I can calculate the area of the triangle in a different way. Do you remember? This is the height, this is the base. So it becomes AC times AB divided by 2. Agree? And then I just simply multiply by 2 and I have my relation. So it was much easier suddenly to shift the way that you are thinking from something. If you want to be able to do this, then you have to work hard. Otherwise, you will not be able to shift the perspective. And then you know that, by the way, this happens in research mathematics as well. There are problems that haven't been solved, for example, wasn't been solved for 300 years, and then suddenly a person, of course that problem was so hard, you cannot say suddenly some person realized. He proved the theorem based on previous works, of course, but at the end he were able to solve that. So I think this is a good exercise, by the way. I think we can use similarity also to prove this, yes? But which pair of triangles were useful, do you think?
The big one and
no, but the point, yes, big one, I don't think it can be, because AB, AC, and BC are all, okay.
Yes, the big
So,
one and the right.
so AC and BC we take for the bigger one, AH and AB we take for the smaller one, yes?
Okay.
So we can actually do that,
Their
yes?
common angle is it?
Yes, so we showed that this triangle is similar to the bigger triangle, but we focused on the first two pairs. If you focus with the first pair and the last pair, which we didn't write at all, it gives rise to this. But of course, I believe that here it was much easier to work this out in this way. Okay, so we stop here and then continue later. So the next lesson is totally new and is more interesting. But this was a review from what we had in Math 1C.